Hello, good afternoon to everyone. My name is Martin Nesládek, and I'm from Czech Technical University in Prague. And the topic of my presentation is application of self-heating method to fretting fatigue test of the CRMO steel under fretting fatigue condition. Yeah, that's I already said. First of all, let me say a couple of words on the self-heating method itself. Actually, the list of methods that you see here contains, let's say, something which we term as conventional methods, and you may say that they are relatively demanding in terms of the number of needed test specimens, time, and money in the end. Even the Locati method that declares itself that needs only one specimen, it eventually requires previous knowledge of a some curve slope, so there is no benefit in the end. So on the other hand, the self-heating method itself declares that, or usually needs one or two samples to get enough data to get a more or less credible estimate of fatigue limit. So that's why that's our motivation why we applied it to fretting fatigue. Self-heating method itself was originally developed on plain fatigue only, and we want to see if it works in fretting fatigue conditions as well. The method takes advantage from thermomechanical coupling. If you cycle the specimen, some portion of mechanical energy dissipates to heat due to internal friction or microplasticity, and it's emitted outside and can be therefore detected by infrared cameras. The progress of temperature when you cycle the specimen is schematically shown here. In the beginning, you can see quite steep increase, followed by a stabilized phase. And if you cycle the specimen above the fatigue limit, you can also observe the third stage, which is attributed to presence of crack and plastic zone at the crack front. So if you do more measurements like this, you can take these stabilized temperature increases, plot them into this diagram where you have stress amplitude on the horizontal axis and those temperature increases on vertical axis. And these points form something which is called self-heating curve. It usually has two regions differing, let's say, a lot by their slope, and the fatigue limit is found somewhere in the transition between these two zones. Why is the self-heating method rapid means of evaluation of the fatigue limit? It's because the stabilization of the temperature occurs after usually several tens of thousands of cycles. So we can run something which is called step test on a single specimen, loaded in blocks with different stress amplitudes, wait for temperature to stabilize, and here we have enough data to find this diagram. Okay, there are many or several methods how to evaluate the fatigue limit from self-heating data. La Rosa-Risitano method, conservative one, long method using two linear fits. And since these methods don't say how many points you should use to fit the one or another line, there are developed some more, let's say, rigorous approaches. My colleagues, when attempting to do so, found that this data are usually well fitted with a coupled linear and exponential function, and they postulate that fatigue limit lies at the point where the difference of the linear and exponential part has its maximum. Now we are getting to our tests. So we run in parallel conventional tests, conventional fretting fatigue tests, if I can say so, to obtain fretting fatigue SN curves, and on the other hand, we run self-heating tests to get the data to compare yeah, this is our setup. It employs simple free proving ring to control the contact loading. We have used these specimens with square cross section and two types of contact pads. The one with single surface, single fret surface with large radii, and the other with two contact surfaces, the so-called bridge type. The idea behind it was to get as large range of contact slips and therefore as large as possible range of generated temperatures in the contact, so that we test the method if it works in different conditions. These are resulting SN curves for the two pads and the fatigue limits evaluated from them. The test conditions are listed in this temperature in this table. Load asymmetry -1, frequency around 130 Hertz, and pressure force around 9 kilonewtons. These data are fitted by the code and Wecht function, which is shown here. Just for information, here is the initial surface. These are photos of the surface damage after the test termination for the single surface pads, and for the bridge pads, illustrating big difference, let's say, not only in damage but in contact surfaces, in contact slips, sorry. Regarding the self-heating tests, we have employed the Optis infrared camera. Specimens were coated with black paint with a declared high emissivity. Here you can see some sample outputs in terms of thermographs and the temperatures in the fatigue process zone extracted from them. The stabilized temperatures from these measurements were plotted to the diagrams. Here on this axis is a normalized stress amplitude, normalized by the conventional fatigue limit. So the point 1.0 should demonstrate if the prediction or experimental evaluation founds the fatigue limit there, that there is a ideal match between self-heating method and the conventional fatigue test. In the case of our approach, there is 5% difference, approximately the same we can say for the Luong's method. In the case of these single surface pads, if we take a look at the data from the bridge pads, yeah, the difference is almost the same for our approach, and here we have slightly bigger difference, around 12%. Yeah, so we might conclude from this that yeah, the estimate of fatigue limit is not that bad, but one might argue that we are sort of breaking the original bounds of application of the self-heating method, which was, as I said, originally intended for plain fatigue tests. So we have decided to apply some numerical procedure to compute heat and temperatures just for the friction in contact itself, to get the stabilized temperatures from this, and to subtract it from the temperatures measured, so that we obtain temperatures that are attributable to intrinsic friction and microplasticity in the material itself without friction in contact. Yeah. So to do so, we have created the models for uncoupled thermomechanical analysis, 2D model for to compute contact slips and shear stress, From their ranges, we have computed surface heat flux, which was then mapped to the contact surface as a boundary condition in the transient thermal analysis. Yeah, this is a detailed view of the model for thermal analysis, sample output, and yeah, here are the stabilized temperatures from this analysis. We have created a set of computations with different stress amplitudes on different levels of coefficient of friction, because at the time of doing this analysis, we didn't have data from digital image correlation. So we have done this parametric analysis. You can see, for instance, that for coefficient of friction 0.5, the analyzed temperatures are higher than the measured ones. So finally, we decided to take, for illustration, data for 0.8, subtracted them from the measured temperatures to get a new self-heating curve. And if we reanalyze it by the methods that we used previously, we get this estimate of fatigue limit. We can see that here that for this single surface pads, the prediction is even slightly worse. This in this case, if we apply this method, the Looms one, there's, I think, no change. For the bridge pads, we were facing even more problems. If you take a look at this data for high stress amplitudes, we get, even for very high coefficients of friction, temperatures still above the measured ones. So only very high coefficients of friction lead to data that can be used to subtract from the measured temperatures. So in this case, we decided that this numerical procedure in this case doesn't make much sense. Yeah. So yeah, this is not very happy ending. Yeah. To conclude my talk, I should say that even with uncorrected data, we get errors something around 5% error, 5%. As regards the difference of the conventional fatigue limit and the one estimated by using self-heating method. Now, a couple of days ago, my colleagues evaluated contact slips and coefficient of friction measured by, or estimated by, data from digital image correlation. We found that they found that the stabilized coefficient of friction is around 0.55. So in the paper, I will hopefully be able to recompute all the data and give more realistic outputs. So that's all from my talk. Thank you.